Yeah, okay.
Okay, great. Um, okay, so good afternoon, everyone. I'm Owen. I'm going to talk about some work that I've been doing with John Links on looking at integrable bosonic models on kind of four sites and trying to construct new families of integral models with some new interactions. So just to give you kind of a rough outline of what I'm going to talk about, so I'm just going to quickly motivate why we're kind of interested in looking at these models, and then give some examples of kind of models that currently exist and what doesn't work to extend them. I'm going to talk about the model we construct in this case and how we did that, and then talk about obtaining the beta ansatz solutions, equations, and some solutions in asymptotic regimes. And then finally, just talk about how we can extend our model to from a four-site model up to kind of an n-site model. Okay. So, okay, so why are we interested in these old atom bosonic models? So I think one reason is that they commonly emerge as kind of the limiting point of experiments. So this is quite a famous paper by the Oberthaler group with this bosonic Josephson junction. So you've got two modes full of bosons separated by kind of a small potential gap. And you get these kind of different dynamic regimes where you either have coherent oscillations back and forth between those two modes or a nonlinear self-trapping effect. And
Sorry, Owen. I
yeah,
think my image is in the way of the top
oh,
left of your slides.
yes.
Uh, is it possible to turn it off in some way?
Mm.
Maybe not. Maybe move them around.
Oh,
Oh,
wait, it's
oh,
gone.
oh,
Yeah,
yeah,
it
thank you.
went, yeah, don't know how that happened. Okay, but this, yeah, so this experiment, even though we've got kind of spatial modes, it's still very well approximated by the two-site Bose-Hubbard Hamiltonian. This is just, you've got some creation operator on one side and creation annihilation operator on one side and the other side. And then, so you've got tunneling back and forth from site to site and then some kind of on-site interaction. And this is kind of a minimal integrable model. So you've got the Hamiltonian and you've also got the number of particles. You got two conserved operators, 2 degrees of freedom, and you can get kind of closed form solutions for the population imbalance and the phase between the two sites. But yeah, so there's often kind of occur as kind of limits in experiments. So the other side of this is what if we want to make technology out of bosonic systems? And so often sort of the simplest cases kind of form the building blocks for kind of more sophisticated technology. So this asymptotic transistor on the left here, you can think of it as just a 3-site version of that 2-site Bose-Hubbard model from before. We've got 3 potential wells, and they're initially separate. And they're self-trapped because there's not many particles in the middle. But if you put particles in the middle, now you would be able to have particles tunnel from left to right. And even if what you're building is a continuous system, so this is a kind of a ring interferometer on the right, you can still use lattice models to approximate the response. So it's useful for kind of limits in terms of understanding what's happening and building things. And it's also a good kind of minimal quantum environment in which to look for new behavior. And so Noon states kind of superposition states where you have kind of a maximum in one observable in one location, and minimum, and vice versa. And these are pretty common in quantum optics because they're super valuable and let you push beyond the standing quantum limit. So even though they've become really prolific for quantum optics, they haven't been super popular in bosonic systems. But quite recently, there's been some progress looking at these with lattice models. So it's a good place to look for kind of interesting and useful behavior. So that's kind of why we're interested in trying to find these families of models, and quickly some examples. So kind of the prototypical model was the Bose-Hubbard model that we've seen before. So you have a kind of an on-site scattering interaction, that K term. So it's particles colliding on one lattice site and repelling each other. An external potential, this mu term, which is like a tilt here. So you've got two levels, you can just tilt them. And then some tunneling between the two sites. So a question is, can we generalize this two-site system? And one option is to try and extend it onto a bipartite graph. And if you can't visualize a bipartite graph, don't worry, because if I mention it again, I'll have a diagram to go along with it. But A and B here are just your partitions. So you kind of got those scattering interactions act on the whole partition, and you're tilting both, like the full sets of partitions. And then you have tunneling, kind of all-to-all tunneling across the partition. And these types of models turn out to be integrable for 3 or 4 sites. So we can kind of extend these beyond just 2. And we're kind of interested in if we can find any other families like this, and what sort of dynamics do they host. But a good question is kind of how you do that. And because you can add any interaction you want to the Hamiltonian, or you can add as many sites as you like. But the real problem is finding enough conserved quantities. Okay. So I'm going to quickly mention some kind of interesting interactions that normally break integrability, but emerge naturally in the model that we ended up developing. And so one of those is tilt. So if you tilt a model, you're kind of, in some sense, you can kind of break a translational symmetry. And so if that was one of your conserved quantities originally, or one of your conserved operators depended on that translational symmetry, the introduction of tilt will essentially break integrability. And this happens kind of all the time. It's not just a bosonic feature. So you've got the Bose-Hubbard model, the Hubbard model, and even in the Ising model. So if you tilt your model, generally you're breaking some symmetry and you will lose integrability. And another one is dipolar interactions. And so on the left here is a 1D Bose gas. So it's just kind of in a tube. You just kick the tube to transfer some momentum. And you get these oscillations kind of out to the edges, and then they come back together. You get kind of persistent oscillations for as long as you're manage to keep the atoms cold. And so this is kind of classic 1D integrable dynamics. But if you take 2 of these kind of tubes of atoms and put them next to each other, and you allow them to interact with dipolar interactions, you'll find that they sort of no longer have these persistent coherent oscillations. So you can kind of break integrability by turning these interactions on. I'm mentioning these because they both of these types of interactions emerge naturally for us. Okay, so I'm going to talk now about what we did. So we're going to kind of construct our general model and walk through that. But the way that we sort of did this was to use a representation of the O4 algebra. And in doing this, we managed to kind of build charges in along the way so that you get to the end with enough charges instead of just adding interactions and then trying to find conserved quantities. Okay, so we started from the kind of 4D, or GL4 4D matrix units, and defined the mirror antisymmetric tensors. And you should get 6 independent elements, and you can span O4. And we have to define a phase factor. So in the end, when you kind of write out your Hamiltonian, if you don't do this, you'll end up with one of your tunneling terms having a negative sign, which is, I guess, sort of like a persistent current, but it's not really desirable. But you can actually you can define this phase factor and just get rid of it. It's good. Okay, and then so we go from those onto a bosonic Fock space using this mapping. So these are the boson creation and annihilation operators. So BJ dagger just creates a boson on site J, and BK just destroys a boson on site K. And this gives us a faithful representation of O4, of the O4 algebra as a four-mode bosonic Fock space. Okay. So in this realization, we can write our generators of the O4 algebra out like this. Okay. So this Ni operator is just the number operator on a site. So it'll just tell you how many bosons there are on that site. And the generators satisfy the standard O4 commutation relation. Okay. We've got quadratic Casimir operators. So you've got the general form here. And these are central in the universal enveloping algebra of O4. This is quite important because if we build a Hamiltonian from the generators, we're guaranteed to get the Casimir operators as a free charge. So unfortunately, we have C1 equals C2, so we don't get two algebraically independent charges for free just from doing this. This is sort of roughly the idea is that if you build with an algebra in mind, you can pick up charges during the construction that you're not looking for. Okay, so kind of explicitly in terms of the generators, the Hamiltonian we can write down as this polynomial. And then we just stick on this u over 2 n squared term. And we just do that because it lets you factor out everything when you go back into the Fock basis. So you can see the explicit form down on the bottom here. We've got an alpha and beta term that act at the tilt. I'll show you in a diagram in a second. I can do that now. We've got an alpha and a beta term. So these sites 1 and 4 get shifted opposite each other with the magnitude of alpha plus beta. The sites 2 and 3 get shifted by kind of the magnitude alpha minus beta. But that's all you need. So you can write a generic tilt for this model, just those two. Okay, so we've got kind of tilts built in, and we also have dipolar type interaction. So this term in red. And they just kind of emerge naturally once you go back from the generators into the Fock space. We've got a kind of that same scattering term as the Bose-Hubbard model, just the on-site density collisions. And the tunneling terms. Okay, so you can see, so the colors here just kind of represent that we're still on a bipartite graph. Okay, so 1 and 4 aren't connected and 3 and 2 aren't connected. So we're connected kind of across, but not within the same partition. Okay, so we've got the Hamiltonian and the number operator. We know that the Casimir operator is central in the universal enveloping algebra. So we've got 3 charges. We just need one more. And this comes from this H bar. So we can exchange our 2 copies of O3. So using the decomposition of O4 or isomorphism to the product of O3 with itself. We can exchange those 2 copies of O3. And that's what gives us this additional 4th charge that we needed. Okay. So we get a set of algebraically independent, mutually commuting operators, observables. So the Hamiltonian, this kind of mirror Hamiltonian, Casimir operator, and so we've got 4 charges and 4. I'm writing the Hamiltonian out in terms of the generators kind of necessitates doing a basis transformation. If you try and work in the kind of the physical Fock space basis, you end up having to commute those generators with all of the creation and annihilation operators. And that can be a bit of a headache. So if you do the basis transformation up front so that you write your basis states in terms of the generators as well, it makes everything later on much easier. So, if you have an initial, any Fock state, then turns out you can write it in terms of the generators. And so this table here just has the full action of on those new basis states. And you just have to check that that's a complete basis. Okay. So we've got our integral Hamiltonian in terms of the generators. And now we have our basis states that are also expressed in terms of the generators. So we're going to try and find the beta ansatz equations and look for some solutions. So to do that, we just take kind of the general n particle state. You can write it out in terms of complex numbers, u and v. So these are called beta roots, but this is a set of complex numbers. And you can write then your general state as a kind of in this product form, just a polynomial in E1 and E2 and those complex numbers. And so we want to find the action of the Hamiltonian on this general state. And to do that, we exploit a differential operator isomorphism with our Lie algebra. And this makes actually computing what those actions are much simpler, because as I said, otherwise you end up commuting lots of B's and B daggers. It gets quite messy. Or you end up having to use generating functions. So using the differential operator isomorphism now saves you having to do generating functions and differential equations later. But just as an example, the action of E1 on this general state comes out to look something like as you see on the bottom. So when you act the Hamiltonian on that general state, you get an equation, or you get an expression out, and it splits into two parts. So there's a diagonal part that returns you back to the same state. And that's this eigenvalue equation at the top. And then you get all the off-diagonal parts. And basically, we assert that those off-diagonal parts are zero, and that gives us conditions on the beta roots or those sets of complex numbers. And so if you find a solution, then you just can substitute those into the eigenvalue equation to get the energy. So you can see down on the bottom here a plot of what those distributions of roots look like. So for a given number of particles, interaction, and for some different tilts. And this is for the ground state. So this is what those roots look like. If we take a look at the eigenvalue equation, you notice that it's in terms of the sum of the roots. So we'd like to find a closed form expression for the sum of those roots. We work in a regime where the tunneling strength is much smaller than the on-site interaction. And then we can partition our roots out into roots that are large, so U is much larger than epsilons, and roots that are small for epsilon. And so we can then get closed form expressions for what those sums are. So the sum of the small roots. You can get the sum of the inverse of the large roots. But luckily, you can also get an equation that relates that to the actual sum of the normal large root. So putting all this together, you get an expression for the sum of the roots. If you take that and substitute it back into the eigenvalue equation, then you can get leading order approximations what those eigenvalues are in this resonant tunneling regime. So I assert that these look ugly, and John says they look beautiful. Let's disagree on that. So you can do the same with the eigenstates as well then. So you can kind of get closed form leading order solutions to those things. And so then you can use those to look at the dynamics. So I'm not going to go into this or dwell on it, but you can kind of plot observables and look for interesting quantum behavior. Yeah. Okay, so we have an integrable foresight model, and we've got some approximate closed form solutions in the regime where the tunneling term is small. But I mentioned that we were kind of interested in general families of models. So I was going to quickly talk about an interesting way to, if you have an integrable model, to kind of generate a whole family of them. I'm just going to quickly go back to the Bose-Hubbard model because it's simpler to work with. It's just a regular form on the left there, defined with two sites. Okay. So the first thing to do is just split a site. So we split site 2 into 2A and 2B. And on those two sites, you can define momentum modes. So there's a zero momentum mode and a momentum mode. Just the phase difference. Then the procedure is basically wherever there's a B2 in the left Hamilton, in the Bose-Hubbard Hamiltonian, the original one, You just substitute in for the zero momentum mode. If you expand it all back out in terms of the actual Fox-based modes, you get a Hamiltonian that looks like this on the left, this modified primed one. You can see that now we have a three-site tunneling model. But if you look at it in momentum space, that phase mode is not connected. So the occupation on that mode is a conserved quantity. So you can add a mode, and at the same time, you can add a conserved quantity. So you can, once you have an integrable model, you can extend it to as many sites as you like, just by adding a new conserved quantity every time you add a new mode using this method. If we apply this to the O4 Hamiltonian that we have been working with so far, we can kind of extend it out to these kind of more interesting graph structures. There's sort of a diamond-shaped structure in the middle and like bow tie type structure. And so the Hamiltonian then kind of factors out as a kind of a direct product of the O4 Hamiltonian we started with, and then you get one copy of each conserved momentum mode. And your integrable charges then are the original 4 charges we had, plus all the conserved number operators in the momentum modes that aren't coupled to anything dynamically. You can get generalized beta ansatz equations. The way you do this is you just define some new effective tilts that account for those occupations that aren't interacting. And you can substitute those in, and you get exactly the same beta ansatz equations, just with alpha effective and beta effective instead of just the. So although you get the same beta ansatz equations, you now have an ensemble of those O4 Hamiltonians. So you get one copy for each non-zero momentum mode. And so you can actually get quite different physics. So just as an example of that, before you do this splitting procedure, just the regular model, it doesn't produce Noon states. So if you start with a Fox state, it won't evolve into a Noon state. After you do the splitting procedure, you can actually see this behavior where as you increase the number of sites, so if you've got one site on each side, but you've got 2 on the top and 2 on the bottom, as you increase the number on the top and the bottom, you kind of get scaling towards better and better ability to produce those interesting and useful quantum sensing states we talked about. But you do actually, that interference kind of allows you to observe behavior that isn't apparent in the regular case. So even though the beta ansatz equations are the same, you get interference between sets of them. It can kind of reveal interesting behavior. Okay, so just to summarize, so we've constructed an integrable tilted 4-site extended Bose-Hubbard model by using the O4 algebra, which is kind of cool considering that tilt and all interactions don't usually associate with integrable models. So, and the beta ansatz equations, and found closed form solutions in the weak tunneling regime, and extended our 4-site model out to kind of an infinite family of models, applying that kind of behavior. Yeah, so it's kind of a relic slide, but so the one-on-one, just the regular model just shows kind of coherent pair oscillations. These extended models kind of show all sorts of interesting things we're still looking into, but they seem promising for generating useful quantum states. Thanks.
Okay, let's thank the speaker. I think we have